In this lecture, we are going to see about the finite square wave. So the potential is defined here in this first equation. So in between the region A and minus A, the potential has a depth of V naught. So the depth is indicated by the negative sign. And in the region greater than modulus of A, okay, greater than the modulus of A, we have potential is 0. So what we have to solve is for states that are for a particle that has energy greater than 0, those are called the scattering states. So we'll solve the Schrodinger equation for that. And for particles for energy having less than 0, values of energy having less than 0, those are called bound states. So we'll start out with the bound state, and in the first region, that is in the region where x is less than minus a, we'll write out the Schrodinger equation and try to obtain its solution. So the Schrodinger equation is written out here. So here there is no potential. So the Schrodinger equation is, this is the Schrodinger equation in this region. It can be simplified to this form by writing out kappa to be, we write kappa is written out as my square root of minus 2me by h bar. So this equation has solutions of the form. So this equation that I have written, that is written out here, has solutions of this form, general form. So this is the general solution. Now we'll have to see what are the physically admissible solutions that are possible. Okay, so we need a solution that is even consistent at infinities. So when we substitute minus infinity, what happens? You see that the first term blows up. Okay, so it is not a physically admissible state, because when you do normalization, we are finding out the value of the integral at infinity. So if you make that substitution, if you find out the value at infinity and if the term blows up, it is not a physically admissible solution. So that's why we are doing this. So we take out the only the second term. So the second term is written out here. This is the solution in this region that we considered. Now let's consider the second region. So the second region is between minus a and a. So it is written out here, minus a and here. Here the potential has a depth of v naught. Okay, minus v naught. So the corresponding Schrodinger equation now reads minus h square by 2m d psi square, second different derivative of d psi square, and minus v naught psi is equal to e psi. So this is the Schrodinger equation. Now this again can be simplified and written out if we introduce a new parameter L and define this parameter to be this term here, square root of 2m e plus v naught divided by h bar. So that is the L parameter, and this Schrodinger equation can be rewritten in this simpler form. Now the general solution we'll have to see again. Now the general solution is given here. Now we'll have to see the physically admissible solution. So now at x equal to infinity, when x is going to infinity, the second term blows up. Okay, so now we take only the first term. So now this is the solution in this region now with that we consider. Okay, so actually this is the solution. So that is for the next region. This is the solution in this region. So it is in the terms of sines and cosines. So this is the solution in this region. In the region minus a to a, this is the solution. And in the region greater than a, in the region greater than a, similarly we have to write the Schrodinger equation, and the solution is written out here, just like we did for the first region. This is the third region. It's very similar to the first region. So but here the second term blows up at infinity, so we retain only the first term. So this is the solution. So now what we have to do is we have these constants. So how do we find out values of constants? We find out by using the boundary conditions. So the boundary conditions here for the problem are, for any quantum mechanical problem when it's solving the Schrodinger equation, psi should be continuous, right? And here d psi by dx, the first derivative of psi also is continuous. At a delta function, it picks up a discontinuity. But here we are having a finite potential, so d psi by dx also is continuous. But you can see that the potential is actually a function is actually a even function. Okay, so the psi that we have can either be odd or even. Okay, so now what we'll do is we'll solve for the even case. Okay, here we'll solve for the even case, and the odd case you can work it out. Okay, so the even case is where we are looking for solutions of this form. Okay, we are taking in this equation that we got, we are taking only the cosine term because the cosine is the even function. So the advantage of this is that we need to impose the boundary conditions at only one side, right? So if you, because this is we're considering for an even function is symmetric in it's a symmetric function. That is what is the even function. So if you apply if you find out at one side by symmetry, you know the other side. Okay, so it is automatically determined. So that's why we are writing out this in a this way. So it is simpler to find out. So we're just applying the boundary conditions at x is equal to a, and psi, since psi should be continuous, we just stitch the solutions together. Okay, we stitch the solutions together. We stitch this solution and this solution. They have to be equal at this point, that x is equal to a. And since d psi by dx also, the first derivative is also continuous, we take the differentiation of these two functions and say at this point these two are equal. So now, using these two equations, we can find the value of kappa. Okay, we can find the value of kappa, and kappa's value is given here. Now, what we have to do is we have to find the allowed energies. Now, and when you solve for this equation, as is in terms of kappa and L. So kappa and L are both are functions of E. So when you solve these equations, you will find the allowed values of energy. So to solve this equation, what we do is we introduce some new notation where we define a new parameter z, which is equal to LA, and z naught, which is equal to a by h bar square root of 2m v naught. So this equation now is rewritten as this equation here. The same equation here now is rewritten in this form. Now this is actually a transcendental equation. Okay, that is, it does not have a solution. Okay, it can only be solved numerically. Okay, so this equation now we can solve it numerically using a plotter. So you can see that the intersection points here, z value is going in increments of pi by 2, and where here the tan z line intersects with the tan z line is going like this, and it intersects with the the term on the right, square root of z naught by z square minus 1. So this term, this line intersects with this line. So the point it intersects is the solution. Okay, so here we have obtained the solutions graphically. So you can see that the solutions are just before integral times pi by 2. Okay, so here it's pi by 2, here it is 3 pi 3 pi by 2. Okay, so it is actually where n is an odd number. So we'll discuss the case here where n is an odd number and the well is deep, when where z naught is large, the solutions are obtained at Zn is equal to n pi by 2, where Zn is a odd number. So here you can see that we've obtained the allowed energies. And when as Z naught shrinks, you can see that there are fewer and fewer bound states, and finally it disappears. So you can see that in the solution here.